Let's turn our attention to another type of catalysis that occurs at an enzyme reaction site. And I'm actually really jazzed to go back to our good friend, this enzyme. And maybe we really should give it a name. So this enzyme in this case is going to catalyze what we call covalent catalysis, which is what it sounds like. It basically means that a substrate or a piece of a substrate is covalently bound to an enzyme to form a reactive intermediate. Let me show you though, this is much easier to see. So essentially, let's picture that this is our substrate right here. It's good looking, isn't it? So what's going to happen is that this substrate, which we're going to call AX, with this group right here that's the kind of silver bobbly being X and this being A. So this is covalently bound to one another, and the Velcro is going to represent covalent bonds. So we're going to say then that our AX substrate binds to our enzyme. And what the enzyme does as it's at its reactive site is that it breaks the covalent bond between A and X. And now what will happen is that A is released as product and X becomes covalently bound to the enzyme. So see there, now we have formed this reactive intermediate in which a portion of the substrate has been covalently bound and temporarily bound to the enzyme. So in comes now the second substrate, which is going to be B. B is going to come in and bind to the enzyme, but the enzyme is then going to catalyze the movement then of what was originally our X onto B. So X will be covalently bound within this enzyme active site to B, and then what will be released is BX. So check the changes that just happened there. We now have a covalently bound substrate BX. We began with a covalently bound substrate AX, remember the purple bound to X. And so essentially what happened was that X, the silver bobbly, was transferred from A onto B. So the enzyme enabled that covalent catalysis.
When we talked earlier about how changing pH can really elucidate the roles of amino acids at the hearts of enzymes, we really didn't see how you would experimentally show that. We talked about how you might vary the pH from below the pKa of a side group to above the pKa of a side group and watch the enzyme activity. Let's look at that experimentally here with an enzyme that is just fantastic. It is called papain.
Papain is an enzyme that can be isolated from the latex of the papaya fruit. And you can see by looking at this picture from the protein data bank, 9-PAP, that it is a cysteine protease. It is a very famous enzyme, and for thousands of years it has been isolated for many different purposes. One such purpose is obviously to help people who cannot digest their own protein. And if you in fact go onto Google, you will literally find hundreds of dietary supplements that you can purchase from various sources, ranging from Swanson to GNC. These are dietary supplements that help people who have a lot of trouble digesting their own protein. But this is not the only application of the enzyme, the cysteine protease. In fact, also it's found in meat tenderizers, of course, again, to degrade the peptide linkages in the meat. It's found in home remedies for bee stings and wasp stings. It's also found, get this, in toothpastes to help degrade protein. So it's found in a huge variety of different applications for this enzyme papain. We're going to look now at some of the chemistry at the active site, and the two polar amino acids that stick their head into the active site and play a role in catalysis in allowing for the degradation of protein at the active site.
And we can determine which pHs allow for the amino acids at its active site to be the most active. So let's look at that. Experimental variations in pH can elucidate the roles of particular amino acids in catalysis or substrate binding. So in papain, the sweet thing about it is that it's known that there are two amino acids at the active site, and their pKa's are actually 4.2 see if I can draw kind of a dotted line up from 4.2. 4.2 and 8.2, so two important polar and ionizable side groups are side groups at the enzyme active site, one with a pKa of 4.2, one with a pKa of 8.2, and we'll just try to get a dotted line for both of those. And if you vary the pH experimentally around these values of pKa, what you see in terms of relative reaction rate or enzyme activity is that below a pH of 4.2, the enzyme activity is fairly low. Now, as you cross that pH of 4.2, you begin to see a pinnacle of reactivity. Head towards a pH of 8.2 and down comes the activity. So we see sort of this peak in enzyme activity, and what we note is that it begins to start to peak above the pKa of the first ionizable amino acid and below the pKa of the second ionizable amino acid. So what we're seeing there is that the peak in activity is actually halfway between 8.2 and 4.2. Those two pKa values divided by 2 is actually 6. So we're seeing that peak in activity right at a pH of about 6, and that looks about like what we've labeled on our graph. So what we're seeing then is that, think about this in terms of the two amino acids. One of them with the pKa of 4.2, if we go above its pKa, then things seem to be most active. So what we would say there, right, is that the deprotonated form of the first ionizable amino acid must predominate in order for there to be activity. So this represents this stretch of time here, and let me use a different color. This region during that time was representing the deprotonation of the first amino acid. And now this, of course, is representing the deprotonation of the second amino acid. So what would be true then, we can just star this and write this down, is that the first amino acid must be deprotonated and the second protonated in order to see activity of the enzyme. So the two amino acids are different in that one must be protonated, one must be deprotonated to really reach that optimum of functionality. So this is a cool way to show what state the amino acids have to be in order for the enzyme to be active. And I think that it's really interesting in papaya, actually, and I'm just going to note this real quick, that this actually corresponds to cysteine 25, and this corresponds to histidine 159. So notice how perturbed their pKa's are because of local electronic environment. So you have to recognize that those may be different than what you might expect for the pKa's just because of the environment around the enzyme active site. So let's go ahead and write all of this down. If there are two ionizable amino acids, so if there are two ionizable amino acids at the enzyme active site and the enzyme is not denatured by a change in pH, then we can make this plot. And for papaya, for papain out of papaya, we can certainly make this plot. This plot, of course, is going to vary depending on the number of ionizable side chains. If we're looking at something that has 4 or 5 different important ionizable R groups at the enzyme active site, we won't see such a nice curve giving away its optimum activity based on just the 2 amino acids. And so here this is partly made nice because there are 2 ionizable side groups, just the cysteine 25 and the histidine.